thanks, Jonah. Thanks for coming on the show. This has been great. Great to meet you finally. This is how we meet nowadays, right?
That's right. That's
so
right.
why don't you tell us a little bit about yourself and your organization and what you're passionate about?
Well, great. Well, it's nice to meet you, and it's great to be talking with you today, especially about this subject. So my name is Jonah Myerberg. I'm one of the co-founders and the CTO of Desktop Metal, and I'm a mechanical engineer.
By the way, I love
degree.
the name of the company. I love it.
Well, great. Well, thank you very much. We wanted to keep it simple. We wanted it to tell an immediate story, and that is the simplification of metal 3D printing. So what's simpler than a metal printer sitting on your desktop? But that's right. We are so we'll get into Desktop Metal in a minute, but just for your benefit, my background, I'm a mechanical engineer. I studied manufacturing and solid mechanics at Lehigh University and Johns Hopkins University. My first job out of college was designing power tools. I love designing things. And then I met my co-founder, Rick, when he was starting a battery startup. And as a mechanical engineer, there's not a whole lot of moving parts in a battery. So I was a little bit nervous and jumping into, energy storage. But it changed my life. It was an amazing experience, and it put me on this trajectory to chase down sustainability that has become my passion. So, I started out in manufacturing and design of kind of consumer electronics, went into energy storage, and then was really looking into other ways to make a difference in sustainability and green tech. Got into water desalinization and water cleaning, and then started to really focus on cleaning up manufacturing, and that's where we are today at Desktop Metal.
Very cool. So tell me a little about the desalinization. What happened there? Was the technology not far enough along for you to work with it, or because that sounds really fascinating?
No,
to me
it was absolutely. So it totally was fascinating, and it was a great experience. This was a company that a technology that came out of MIT, focused on cleaning up the wastewater that was being produced at fracking sites. And fracking gets a bad name because really it's a dirty process, and part of the reason is because you're putting clean water into the ground and making dirty water, and that's that's never good. So if you could recover that water and reuse it, or recover it and release it, that's what we focused on. And so I spent a lot of time in Texas deploying these desalinization plants. We call them desalinization. It's not ocean water. But the water that comes out of the ground during a fracking site is very salty, and so one of the biggest dissolved solids that you need to pull out of that water is salt. But then there's a lot of other things as well, a lot of other minerals and a lot of other chemicals. So you clean all that stuff up, and then you make the water clean enough to release into the environment again, and it makes fracking look a whole lot better than it did.
Very cool. Very cool. So you transitioned to Desktop Metal, and you said manufacturing. Is that because it's your past? That's where you came from, your historical history. You've always been interested in manufacturing, or what brought you into the manufacturing space?
Yeah, absolutely. I was a mechanical engineer, always studying manufacturing and manufacturing technologies, processes. And when I was in school, we studied 3D printing. I'll use study in quotations. 3D printing and additive manufacturing were really just a concept in the 90s for prototyping, and it really wasn't taught as a mainstream manufacturing process back then. So I was always kind of a customer of 3D printing, and I immediately saw the potential as a mechanical engineer designing in the digital world. I needed to then get those products out of the digital world and into the physical world, and 3D printing, was the answer back then. Wasn't ready, and so we had to wait a couple decades before we could really take it to where we're taking it now.
Don't you hate that everything always takes longer than you think? It's like, oh, this is so cool. We need it now, and it just takes forever.
Absolutely, it really does. And you know what, we tend to overestimate the short term. We're like, this is going to happen next year, and underestimate the long term. And we really need to rebalance the way we think, because it will happen. It does happen. It just takes some time. It's not going to be tomorrow, but it will. It'll be faster than we think, especially with guys like Elon Musk out there pushing for it. To happen fast. So I started out in manufacturing, and like I said, I went into energy storage with designing next generation lithium-ion batteries. And these were batteries and battery technology that enabled our customers to do things they've never been able to do before. Electrify cars or grids, and really take energy storage into areas where it could be the most beneficial, for changing the environment, changing the world, sustaining green tech. And the electric car really led the way. This is 20 years ago. The electric car was going to save the world, right? It was like all of our pollution comes from electric vehicles, and as soon as we have a good sustainable electric vehicle, then we'll make a big difference in carbon emissions and everything there. And it's working. It really is working. We're 15 years later, it's working. But what I discovered along the way is that, yeah, sure, the automotive industry and vehicles and highways, transportation, logistics, it's a big part of it for sure. But if you take a look at other areas like water, I dove into water, and water was an important piece of the puzzle here as well. But when you really take a look at it, manufacturing can make an even bigger difference, right? Oh, yeah. Making manufacturing greener. And additive manufacturing digitizes manufacturing in a way that that isn't there currently, right? Traditional manufacturing requires a ton of investment into tooling. It drove this third industrial revolution to consolidate all the manufacturing in a low rent country and develop this supply chain that was like materials in, materials out. This non-digital analog type of manufacturing it can be improved significantly through additive. So additive being a fully digital process means that we can send files electronically anywhere we want. We can distribute manufacturing back to countries where you want it to be, where the end use products are being used, next to the assembly factories. Reshoring all that manufacturing simplifies the supply chain.
It's a lot cleaner, right? I mean, additive manufacturing is way cleaner than current processes, right?
It's highly optimized. Exactly. All of the tools that we use in current traditional manufacturing are now digitized, consolidated, put into a server instead of a warehouse full of shelves where you have physical tools sitting there rusting, obsoleting. You now have digital tools that can be easily maintained, improved, and updated. And then, I call them digital tools, but they're really just build files, right? They're build files that are designed for additive, and then can be continuously improved, and the design can be continuously changed and updated, and there's no waste stream there.
Fabulous. So what happens? So when you talk about sustainability, let's say you do create the part or whatever, and then can the part then be recycled as well? Like once it's been improved and replaced, can you actually take that piece that you've created and recycle that back into the process?
Yeah. So it's a great point, and it's one of the reasons why we started in metal, because the materials that you use to develop your product or design your product, manufacture your product, they have the biggest impact on the world. And we're seeing this right now in electric vehicles. It's like, okay, sure, we're making the electric car greener. Electricity is making the car greener, but what do we do with that battery that that we've spent all this energy and time into, and we put it
exactly.
Into
I mean, that's always been my issue with electric cars. It's like, what happens at the end of life? I mean, what happens to these batteries? I mean, where are they going to go? What are we going to do with them?
Yes, exactly. And so the UN has launched this initiative a number of years back, the circular economy, the circular vehicle. And it's challenging everybody, all of the vehicle designers, and then the life of that vehicle beyond the road. What happens next? And these battery packs are now being removed from the vehicle and put onto the grid, because there's still a lot of life back in it, right? You start you buy a car, you buy a Tesla or whatever, and it has 300 miles per charge on it, and that goes down as you run and cycle that car. The batteries are reduced. So by the time it gets down to 250 or 200 miles per charge, you're a consumer, you're upset. I need a new car because I'm not going as far as I want. But there's still 2/3 or more of that energy storage left in that vehicle. So put that somewhere else. Use that somewhere else. Have a farm in which you have wind tech or solar tech charging that battery and depleting that battery at a much lower rate than you would on the car on the road. And so there's an extended life there for that battery. The same thing is true on every component within the car, and that's why we focused on metals. So metals are infinitely recyclable as opposed to plastics, right? Like you can take these polymers and we can put them in the recycle bin, and we can chop them up and turn them into something else. But usually that's where it ends. Usually you take, these polymers and turn them into a carpet or turn them into a textile or something that like is the next level down of that manufacturing process. No longer virgin polymers that can be, made into very critical applications. It's secondary, it's recycle. And that's the problem. Is we need to, as an industry, begin to focus on recyclable materials. And the start is metals, right? So metals, we can melt them down and reuse them forever. And that's the big push here in the circular vehicle. How do we lightweight the vehicle, simplify it, and use recyclable materials doing it?
Is there a particular metal that's preferred? Or, I mean, I'm assuming there's also new technology in the metal space to create new alloys and things like that. I mean, are we seeing new things there that will make cars lighter and make parts better?
Yes, absolutely. So there are preferred materials or preferred metals depending on where you are in that vehicle or where you are on that engine or spacecraft or rocket. There are certain requirements, whether it's temperature or strength of material or ductility, resistance, to cracking. There are definitely preferred materials, and we're seeing, for instance, steels being used in high strength, high temperature applications, and then materials like titanium, which could replace steels with this strength and at a lower weight. But titaniums are traditionally very, very expensive. Now, titaniums, are usually come in a big block or rod form, and are reduced right through subtractive manufacturing, where you have a lot of waste generated. You're taking this really, really expensive material and you're machining it, down, and sometimes removing up to 90% of it. This is, there's some aircraft applications that remove more than 90% of the material that you want to use.
Insane.
And
that's insane.
It's insane. And so this is really where additive comes in and immediately reaches parity and says, hey, we're going to print instead of machining, and we're going to use only the material that we need to use. And if you have some critical features, holes or surfaces that really need high precision, we can machine those, but we're taking off a fraction of the material that you would normally scrap for that process. So additive manufacturing kind of enables these very expensive, high value, high performance materials to be manufactured in a much more efficient way and unlocks their use in other industries. Initially starting with medical and rocket and aerospace, where they're needed and you can afford them. But the automotive industry would love to use it. The power tool industry would love to use titanium.
Oh yeah.
So this is, and that's right where it's going.
So I'd love to know. So I can understand how the polymer additive stuff. I've seen in 3D printers, additive 3D printers make plastic stuff. But I can't imagine how do you make metal stuff out of 3D printing? I mean, is it some kind of is it like soldering almost, like where you're melting, making the metal fluid, or how does it actually work?
Yeah, so it's a great question, and there's not one answer for that. So metal 3D printing has been around for over 20 years now. It's not new. We didn't, Desktop Metal didn't invent metal 3D printing, but what we're doing is we're optimizing that process. So there's a number of different ways that you could print metal. And when I started my career back in Black & Decker, this was more than 20 years ago. In the 90s, we were utilizing 3D printing and 3D printing of metal. And I'll use quotes again. It wasn't really 3D printing of metal because we 3D printed a polymer. Back then it was an SLA form, very, very weak, looks like, kind of feels like, fits like model. We coated it with ceramic, and then burned it out, and then poured, aluminum into that mold. So we basically created an investment cast by using printing to create metal parts. So that was the beginning of kind of metal printing. That evolved into what we see right now, which is called direct laser melting, which is DMLS. And that is taking a laser, firing it into a powder bed and melting. And that's closer to what you described kind of with the soldering, right? It's taking that powder up to its melting temperature, creating a melt pool, and essentially drawing a picture with a laser of that part over and over and over and welding itself together. It's It's a welding process. And unfortunately, a lot of really good alloys don't process well with laser melting. They tend to crack, they expand, and they contract.
Yeah, I
They're
was going to
not
say,
good
doesn't that do something
alloys.
to the strength of the actual metal when you do something like that?
100%. It changes the grain structure. And so when you look at a cross section of a laser melted part, it looks different than any other cross section you've ever seen of a metal manufactured part. It's welded up, kind of voxel by voxel, from a micron powder all the way up to a huge multi-inch sized part. And so the grains of that are extremely unique. They have, they've been welded together. They have crazy different properties. And it's not to say that they're bad properties. If you can get them to get these materials to weld and not crack, they have usable properties. That's no problem. And in fact, in the early 2000s, companies like GE grabbed onto laser melting processes and said, "This is the future. We're going to develop it." They invested billions of dollars in these companies and built plants around the world where they could make jet engine components. And it's fantastic. I love what they did because they were an early adopter of additive manufacturing. They said, "We want to print parts because we can see the advantage. This is what's available to us. This printing process of using lasers and firing into metal powder beds. We're going to take it." And they took it and ran with it. And over the first 10 years of that history, they developed it significantly into a really rock solid processes that they could make certain components using certain materials. And it was great. It was great to watch. When Desktop Metal came along, this was a decade after GE had grown that business using laser melting, and we said, "This is great, but you're developing larger and larger machines, more and more inexpensive processes, focused at aerospace engines. That's not what the consumer wants. That's not what the vast majority of manufacturing needs. We need it to be cheaper, faster, more affordable, and more accessible to companies like the automotive industry, companies like I started Black & Decker. I wish that we could be printing power tools in metal, but we could not afford that process. That was crazy. We need $1 billion factory that prints metal. Only GE and aerospace companies could afford that. So we launched in a different direction, and we said, okay, we're going to leverage powdered metallurgy, because powdered metallurgy is a great medium to work in, right? It's like flour, but it's steel, or it's titanium.
Interesting.
But it's flour, and so it's very high resolution. You can build very high resolution structures and geometry with that powder. But instead of melting it with a laser, we leveraged high volume, high speed inkjet processes. So literally printing presses. So you think about a printing press that prints at 5 meters per second. And paper is just running over, and huge high resolution billboards and picture, like photo quality images are created every day at 5 meters per second using these printing processes. So we developed our own inks that could bind the powder together. We leveraged the powders that the metal injection molding industry was using and has been using for the past 50 years. So these powders, actually powdered metallurgy has been around for 100 years. And it is not typically melted with a laser. That was new. What it is typically done is it's sintered together. So you form the part into what we call a green part, which is just a bunch of powder, and then you put it into a furnace, and the furnace drives out all the porosity. It grows the grains larger than the powder size itself. So you end up cross-sectioning these parts, and it looks like a casting, right? It looks like
the part
was forecasted.
So cool.
There's
it's almost like ceramic. It's almost like you're making ceramics, but you're creating metals out of it.
You got it. That's exactly right. It's like the ceramics process, and metals are even better than ceramics at sintering. Now that it's more difficult, like ceramics, because they're an oxygen containing material, right? So they're all oxides of some sort. Those ceramics we can fire in air, and they love the fact that you're in air, a nitrogen air mixture, a nice nitrogen oxygen mixture here, that air, they fire perfectly fine in that. But metals don't like to oxidize. We don't want them to oxidize, I should say. They love to oxidize, but we keep the oxygen out of them during the sintering process. So if you can get the oxygen out of the atmosphere, sinter in vacuum or in inert gases like argon and nitrogen, then you get a very high quality metal. And that's what the powdered metal industry has been developed on for the past 100 years. 50 years ago, metal injection molding was introduced, where you mix metal with polymer and injection mold it like a plastic. And these parts come out of the tool, they're half metal and half plastic. You burn off the plastic and then you sinter the metal and you end up with a really nice, high quality steel part. So we leveraged that plus the high speed printing press technology. And now we're mass producing parts that are glued together and go right through that same sintering process, drive out all the porosity and end up with a solid metal part.
Wow, that's fantastic. So how long did it take you to develop this process?
So it took a few years. We were founded in 2015, and we launched our first product in 2017. And now we're adding to the portfolio. We're on this huge growth ramp because I think that everybody has feels the same way that we do. They wanted access to metal 3D printing, and they didn't have it. And so now we're giving customers who have been sitting around waiting for it access to it, and other customers who have said, I'll never be able to print metal, the same type of access. And now we're entering industries that we never thought we'd get into. Like, for instance, we didn't launch the company thinking that we'd go print jewelry, but printing gold, silver, platinum. I mean, there's a huge industry out there that is ready to print those materials. So we developed binders that would stick those powders together. We're developing atomization processes to make gold powder and platinum powder and silver powder. And that industry is taking off. So that's becoming a huge pillar of the additive manufacturing industry. Then you've got companies like Ford, General Motors, BMW, who are in from the start. They said, we want metal 3D printing, we just can't afford it, and now they can. And so there's a lot of areas that we're diving into that we didn't even think we'd be in.
Well, that's amazing. That's totally amazing. So can you tell me a little bit about, you're saying that what they had to do instead, there were much more expensive processes. So if I wanted a part made in the previous process, like what kind of difference would you say? Like if I went to company A and then I went to you, what kind of variance would there be in the price of building a product like that?
Yeah. So there's two aspects to consider. So there's what you just described, like, okay, we've got this part and I need to decide how I'm going to make it. I'm going to either print it or do a traditional manufacturing process on it, which could be machining or casting or whatever. So let's say you have that part that can be machined or could be cast. You use jewelry as an example. So the jewelry process has traditionally been to take a piece of wax and to carve it. And that's what the jewelry designers of the past have done. They've taken wax, they've carved it into the shape they want. They coat it then with a ceramic powder material, like pottery, and they then melt out the wax, and then they pour in their gold or their silver or whatever it may be.
Yeah, so they create a mold for it, and then they pour the metal into the mold, right? It's basically just a mold.
You got it. You got it. Exactly.
Yeah.
That's right. Just a really cheap, kind of inexpensive, tool. But that takes time, right? And what happened over the past 20 years is that digital design or jewelry design became digital. Everything is created in a 3D environment on your computer. You're able to create very complicated any geometry that you want. You can create in the virtual world. You refine it. You can show it to your customers. You can experiment with it, and then you need to get it out of the digital world. So 3D printers evolved into polymer printers that could print plastic or could print wax. And so you could, instead of carving that part, you could then create it out of wax. And so you could print it and then go through the same process, create the mold and then pour the forecast. And so what we're able to do is directly print that metal. Instead of printing a mold or printing a polymer piece first, you directly print that metal. And so that toolless manufacturing, applies to a lot more than just the jewelry industry. But toolless digital manufacturing, going straight from the digital environment to the physical environment in one step, is so valuable. And so that's one way to look at it. There's this concept of design for additive, right? And so by taking what we just described, is you took an existing design that you could make any way, a number of ways, and you chose to print it. Okay, great. Reality is we're about parity with doing that right now. If you take advantage of additive manufacturing and 3D printing, you can redesign your part to take advantage of it. Like you can put features in that part that can't be made any other way, like cooling channels that are you can't touch with a drill bit. They just go deep into the part, or they turn around. This is embedded features. And once you begin to adopt this design for additive, this spirit, you can create so many different and new designs and take advantage of more than just what we described, which is like kind of speed or cost. You can do things that are just impossible any other way. You can take 10 parts and consolidate them into one. 10 parts that were designed to be an assembly because they can be manufactured that way, and then they're bolted together. Well, why not just design one part that can be printed that is that assembly? And once you adopt additive design for additive, it's really hard to go back, because in order to go back, you have to split up the parts. You have to start adding bolt holes again. You're becoming a lot less efficient. And this is where additive manufacturing today is enabling the rocket industry. The engines of yesterday were a million different components, all pieced together, super complicated, hard to maintain, and having reliability issues because they were all different parts bolted together. The rocket engines of today are a fraction of the size because they are completely consolidated, 1,000 parts into one. And they are now much more efficient, much more effective, and they're enabling this reusable rocket, this reusable engine that we're seeing, SpaceX take advantage of. And SpaceX is the lead name, but there are tens of names of rocket companies and engine companies that are right behind them because the space is blowing up, and additive manufacturing is enabling it.
Wow, I love that concept. But is it hard for designers who are currently out there, like say the majority of people who haven't played with this before have always gone with regular manufacturing? Is it difficult for them to make that leap into additive? Because I totally understand what you're saying. It's like going from functional to object-oriented programming. It's almost impossible to go back, right? So is it difficult for people to actually make the leap into it?
You're absolutely right. It is it's a skill. We as mechanical engineers design the parts as much for their function as for their manufacturing process. Right? If you design a hook, a hook or a bracket, you know what you want it to do, you know how you want it to function, but you immediately have to ask yourself, how am I going to make this? And so you then steer the design in that direction of like, either I'm going to bend sheet metal, or I'm going to, mill it out of a block, or I'm going to
I mean, the practicality is almost more important than anything. I remember my old engineering classes were the same thing. It's like, you can make a fanciful structure, but if you can't build it with using our current process, then you got to change it. But it sounds like that's changed now. But go ahead.
Yeah, you're absolutely right. And sometimes it influences the design more than the actual functional design is the design for manufacturing. So the consideration of design for additive has only been started to be taught in schools in the past, I don't know, 10 years. I wish that I had learned about this as part of my design for manufacturing courses in university. And we had them, right? You go through a manufacturing course, and a big part of that manufacturing course, not 90% of it is design considerations for the manufacturing process. I'm going to injection mold this, and it needs to have draft angles. It needs to have
exactly. You almost have to start backwards. You say, here's my limitations, and then you got to work within this little box, right?
Yes. And so you study that hard, and you know it. And once you know it, it's great. You can think about any design from a manufacturing standpoint, and then design it. And it kind of it constrains your design, which is great. I love constraints. They constrain your designs, and you can design it and move on. And so the designers of my generation or older generations, they grew up on that design for manufacturing, not including additive. So it's a hard transition at our level to say, at older engineers to look back and say, okay, we're going to relieve all these constraints and start thinking about how to design this from scratch. Like, what if I didn't have to put draft angles? What if I didn't have to maintain wall thicknesses? What if I could do anything I wanted to do? There are still rules on additive manufacturing and design for additive. that need to be taught and need to be learned. And they're different for each of these processes that we've been talking about. But today's engineer, it's like a generational change. And that's why this is all kind of coming together as like the perfect storm. There's this generation, iPad, iPhone generation of engineers coming out of school now that have, that they demand instant gratification. They're demanding 3D printing. They need their physical part out of that computer tomorrow. And so they're learning the design for additive from scratch, which is fantastic. They're saying, okay, hey, if I want to print this, which I do, I need to know the best way to design it. And they're learning. And so it's happening. It's happening, which is fantastic to witness and experience.
You almost need to bring the artists in, because like the artists are like, oh, they're already outside of the box and the engineers are inside the box. So if you like meld those two things together, and then you get some new stuff, because breaking out of that mindset is really difficult.
It's so difficult. And you're absolutely right to bring in designers and artists, because industrial design, that's one of the push pulls that you experience if when you go through manufacturing, real world manufacturing challenges. You have designers who want the product to look a certain way, and they're fighting with the engineers who are designing that product and saying, I can't give you that. Like that's a very difficult thing to achieve. It's going to be very expensive if you want that. It's going to be bigger than you want it. And so now now we're starting to get along better with the designers, starting to say, learn what is more possible.
Fantastic. I love it. This is great. So I love this because it's sort of, I'm a huge Star Trek fan, and I'm like, oh, we need replicator technology. And this is like it, this is replicator technology for metal things. But so how big can you make, like, what's the largest part that you can make using your tech?
Yeah, so in metal technology, and I have to say that Desktop Metal is expanding our tech. We're joining with other companies that that have similar visions, either have a play in metal or in polymers, or something that we can put together in concert, and and more of a 1 + 1 = 3 type of relationship. But with metals, focusing on metals, which is super exciting. The process really dictates how large the parts can be. And there are metal printing processes right now that almost have unlimited size, right? There are robots on cranes that you can imagine, like a cable or a big wire coming in and melting that wire and depositing a bead of weld. And this is how some of the rocket companies are building their fuel tanks, for example, is to basically weld them up into giant structures. You can use much more effective technologies like titaniums or super alloys, and you can build giant, almost seamless structures that were otherwise had to be fabricated in a totally different way. Take much longer. The way that, like, the space shuttle took decades to complete, and you now have SpaceX that's launching like rocket after rocket after rocket each year, and it's because that time scale has been compressed significantly due, thanks to being able to go from the digital space to the physical space so quickly right now.
Fantastic. So it's time to think like a futurist. We're taking 2031, 10 years from now. I mean, do we see homes actually built with your printer? I mean, what can we not build with that thing? It sounds like it's almost too good to be true. Would it be like a $1 billion home if I built a home with your 3D printer?
Well, no, homes is a great example, and we're already exploring homes, right? So 3D printing of like cement structures is being done. Metal structures is being done. Matter of fact, there are tracts of homes in different countries that are being 3D printed because they are able to efficiently produce very simple or even very complicated shapes very quickly, right? Entire tracts of homes. You can imagine a crane coming in, on a track and printing a home after home after home after home.
I've seen videos and images of that. It's phenomenal. I love it.
Yes, absolutely. Love it, love it, love it. And these are the types of technologies that we're going to take with us to Mars, right? That's what when we go to Mars, we're not going to bring a couple pallets of lumber. We're going to bring, a printing machine that can set up and use the natural resources from the planet to, produce structures. And maybe it's not the entire structure, but it's the foundation, the skeletal structure of these foundations can and should be printed with local natural resources. So that, that's happening here on our planet. That's happening. That will happen on the moon. That will happen on Mars. I mean, that is the way that we, efficiently travel and build.
Yep. But it sounds like nothing's really stopping us. I mean, the technology is there. I mean, what's holding us back from using this more? Is it still cost? Is it a lot more expensive? It sounds like it's not a lot more expensive to do this additive manufacturing.
No. So today, and the reason why we are in the growth stage of our life right now is because today we have achieved parity with traditional manufacturing, where hey, you can do what you were saying before. You can take a look at a part and you can say, should I invest in casting? Should I invest in machining? Should I print it? It's we're all basically the same price, and the same with home manufacturing and building bridges and homes. You can argue, and you can make a very good argument that 3D printing is as affordable as any other of these manufacturing processes, and we're just at the beginning, right? So what happens as you go up, economies of scale, and the ecosystems around you begin to grow and optimize, you had an exponential growth curve, and the adoption rate increases, the costs come down. So the fact that we're at parity right now means that we've hit the tipping point. We're, everyone's in. It's now a reality, and this is what we're calling additive 2.0. This additive manufacturing has been around since the 80s, right? The early patents were in the 60s and 70s. For some of the first machines came out in the 80s, and they were known to be expensive and slow, maybe producing looks like, feels like models of components. But we've evolved them over the past 20 years to today, where we've reached parity on manufacturing costs, and the performance of the parts is the same as mass produced. And so we're entering the second stage of additive manufacturing, where we can begin to really mass produce for real applications, for the mass production applications today that were off limits yesterday.
It's fantastic. So what are there specific areas that you think there should be more expansion in coming up?
Yeah, so absolutely. So today, as I mentioned, we're enabling these reusable rocket engines, reusable rockets. We've begun to distribute manufacturing around the globe. So your companies can put additive manufacturing wherever they want the parts, not consolidated in a low rent country, but expand it and reshore it back here in the U.S. I mean, jewelry market, another great example. Jewelry hasn't been manufactured in Manhattan for 50 years, but that's where it started. I mean, these jewelry manufacturers who were building there, and it's just been unaffordable. They would love to bring it back to areas like that, take it back into the U.S. So that is happening now. If we look at in the short term, we're going to see a lot of other technologies become more viable because of that. 3D printing is enabling carbon capture technology and other green technologies. Organs can be printed now. So medical applications that were unheard of in the past. And this was, 3, 4, 5 years ago, when these scientists and engineers at Northwestern University printed ovaries for the very first time. They implanted them into mice, and the mice reproduced with those ovaries.
That is fantastic.
Demonstrating that it's amazing. So you can imagine the implications that can have on the human, but that type of technology takes years to get approved for humans. So, mice are reproducing for the past 5 years using printed ovaries. We'll see that emerge over the next 5 to 10 years in humans. And it won't just be, ovaries, it'll be other organs, other organ repair, other, areas where, 3D printing is being qualified because right now it's capable, but we're now fully qualifying it. I think, the fusion technology that we're seeing right now, fusion technology is coming, and fusion technology is being enabled by 3D printing as well. The types of heat exchangers and complicated geometries that are required to capture the plasma and the magnets that are required for some of these fusion generators to operate, that is being unlocked through the use of 3D printing. And like we talked about, like building structures on other planets as we travel there. Like Elon wants to go to Mars, and he's going to, and I believe that he'll take a 3D printer with him when he goes. And that's, that may be 10 years from now, that may be, 15 years or 20 years from now, but that's what's happening. And if you look even further, I mean, now you're talking Star Trek Replicator stuff. I mean, we're kind of already there with 3D printers, where you take a base material, a metal powder that could be anything, and then you basically put it through your printer and you create what you need. And that's going to be really critical for space travel, right? Once you get up in a rocket and you're on a mission that takes 100 years to get from point A to point B, what do you have up there with you? You only have what you took, and maybe some energy from the stars around you, right? So you have almost unlimited energy from the stars, but what do you do with that energy? You're not producing mass, so what you need to do is recycle that mass that you brought with you. If you need a spare part or a wrench, you print what you need, and then you recycle it back into the dust, right? You recycle it back into the powder. And so you don't have a socket set up there. You have essentially a socket set on your server. And what you need is what is printed, and then you use it, and then you put it right back into the digital environment.
Exactly. So, I mean, the full-on replicator technology is taking any kind of mass and turning it into any other kind of mass. But if you think about it, if you just had different chunks of mass, you had proteins, carbohydrates, you could create food. If you had metal, you could create parts. So you almost need different kinds of masses. But it sounds like we have the technology to take those different kinds of masses and turn them into something else that's either edible or usable or whatever. And then all we need is the rest of the circle to be able to take those proteins and push them back into the system again. But it sounds like we're really on our way. I mean, based on what you've been talking about, there's really nothing stopping us but sort of cultural change. Like how quickly can I get my fanciful metal designed by myself house, that doesn't look like sort of like the car that Homer Simpson designed in my neighborhood.
That's right. That's right. That's exactly the way to think about it. You're absolutely right. How do we recycle and reuse all of that, all of that mass that we have available to us into the structures that we want? And that's the way to be thinking about it today on Earth. We're lazy here on Earth, and we make what we need and we throw it away into a landfill. But over the course of the next 20 years, sustainable green tech, recycling, carbon capture, this is going to be the focus of technology. We need to figure out how to be more efficient here on Earth, because once we get up into space, there's no other answer. You have to be.
Yeah, absolutely right. It's interesting you say, like, because it's like the constraints are there, but we can use those constraints here to make life better here. So it's
exactly.
Phenomenal. I love it.
That's
all right. Well, this has been great. Thank you so much. So if somebody wants to get in touch with you, what's the best way? Just go to desktopmetal.com, or are there any?
Absolutely, yes.
Yeah.
Check us out at desktopmetal.com. We always, link up with us on Twitter and LinkedIn. You can find me on the same platforms. Please come to our website, desktopmetal.com, and check out what we're doing. Really exciting stuff.
Fantastic. Well, thank you so much. It's been great. Thanks,
Thanks,
talking to you.
Yeah, great talking to you too. Thank you, sir.
Talk to you later.